Please title these notes Integrals 1 Notes, Left and Right Riemann Sums, and write today's date. By the end of this lesson, you should be able to estimate a definite integral using left and right Riemann sums to approximate the area under a curve. So let's revisit for our second the two main branches of calculus. We've got the derivative, which involves dy dx, f prime of x, and in general the slope of the tangent line. And we've got the integral with this symbol involving the area under a curve. We've already explored the techniques for finding derivatives. Now we're going to turn our attention to integrals. It turns out we're actually already halfway there because we know how to find antiderivatives. But mathematicians didn't know when they were playing around with taking derivatives and then asking, hey, what happens when I undo this thing? And taking antiderivatives, they had connected to another seemingly very different problem. And that problem, believe it or not, was how to find the exact area of strange shapes. So at this time, there was a group of mathematicians working on a completely different problem. And for them, their original problem was, how do we find the area under an irregular curve? So by irregular curve, we're talking about something like this, where it's not, a clear circle, it's not a triangle, it's got this weirdo bubbly lumpy shape. And what we're going to do for a few lessons is go back and look at the discoveries mathematicians made while they were working on calculus from this very different angle. And for now, this is completely separate from the derivatives work that we've done so far and the antiderivatives work that we've done. Mathematicians on this, like I said, in completely separate realms. We'll see how the two branches of calculus connect in the fundamental theorem lecture in a little bit. So I'm just going to mark this down here, antiderivatives. Later. To the area problem. Please title these notes in. And the key brilliant idea that mathematicians had was that we might not be able to find the exact area under this using our geometric tools, but we can approximate it by drawing a bunch of little shapes that we do know how to find the area of. The easiest shape to work with is the rectangle, so mathematicians came up with the following strategy. So essentially what mathematicians did is they said, I don't know the area of this, but I can find the area of a little rectangle like that. And if I I draw a whole bunch of these little rectangles. These should be going straight down. If I add up the areas of all these rectangles, it's not exactly equal to this curve, but it's pretty close. It's certainly closer than me just looking at it and trying to estimate it. So what these are called, this technique of doing a bunch of little rectangles, finding their area and adding them up, these are called Riemann sums. Essentially what we're doing is we're saying that the area approximately equals this one's base times height plus this next one's base times height, and so on down the line. Find the area of each, add them up. So the interesting thing is that this gets us fairly close. But there was another sort of discovery that got us even closer. And it's this. If the rectangles become infinitely thin, so I'm going to try to resketch this curve that's up here from A to B. This is x, this is f of x. So it looked something like this. So I'm going to attempt to draw infinitely thin rectangles, so just like that. I'm having to draw them a little bit separate. But if these rectangles are infinitely thin, then these little gaps that we saw up here or over here where it didn't quite match up with where the rectangles didn't quite match up with the curve that had been drawn, those little gaps go away because basically our infinitely thin rectangles are just touching at one tiny point on the curve. And so if the rectangles become infinitely thin, the sum of their areas exactly equals the area under the curve. And so what mathematicians came up with was this. This S, it's a big S, it stands for summa, or add up. This little a and this b, these are our bounds, they're called, so this is the starting x. The ending x. And then what we have in here is going to look really familiar, f of x dx. But what's really interesting about that is what it really represents. This f of x is the height of the infinitely thin rectangle at some value of x. Because that infinitely thin rectangle, it basically just ends at a point on the line. This dx just stands for an infinitely thin width. So what we're seeing here is that the height of the infinitely thin rectangle times an infinitely thin width gives us the area there, and then we add up all of those rectangles starting at A and ending at B. We'll learn how to find these exact areas in later lessons. As you might guess, it does indeed involve the antiderivative, which is why we have the same symbol here that we've worked with before. But what we're going to be doing for the next two lessons is saying, if before we get here, if we go back to this, where we're just approximating it using rectangles, what are the different ways that we can approximate this area? And that's where we're going to talk about Riemann sums for this lecture. There are four types of Riemann sums. We're going to start off with two today. And so we can approximate the area under a curve using what are called left Riemann sums or what are called right Riemann sums. And basically the difference is that with left Riemann sums, the rectangle's left corner touches the curve, and logically enough, for right Riemann sums, the rectangle's right corner touches the curve. So let's get out a curve here. You can go ahead and tape those, and you're going to have to sketch them out. They're the same thing. And what I'm going to have you do is I'm going to have you estimate the integral from -1 to 3 of f of x dx. This is f of x right here, and that will be using a left Riemann sum. And over here we're going to estimate, same thing, integral from -1 to 3 of f of x dx, but instead we're going to be using a right Riemann sum. So all that this means is it means that starting at -1 and going to 3, we're going to have a bunch of little rectangles. So let's go from here to here, here to here, here to here, here to here. We'll know how to pick this a little bit later in the lecture. And in each of these intervals I'm going to make a rectangle, but I'm going to draw it so that the left side of the rectangle touches the curve. And then I just finish off my rectangle. It's okay if it's outside. And so here, for this, here's the left corner touches, left corner touches, left corner touches. Now I'm going to estimate that area by simply adding up the areas of each of these rectangles. So like this rectangle has a width of 1. In fact, they all have widths of 1. The height is 1, 2. Here the height is 1. Here the height is 2 again. 1, 2, 3, 4, 5. Here the height is 5. So I'm just going to do length times width for each one. So this first one, the area is 1 times 2. So that's area of first rectangle equals height times width. Then I'm going to add the area of the second rectangle plus the area of the third rectangle plus the area of the fourth rectangle. So my answer is that all of this approximately equals, when I add these up, 2, 5, 5 over here, 10. Right, like that. And over on this side, I'm doing almost exactly the same thing, same interval, from -1 to 3. But now when I draw my rectangle for right here, I want the right side to touch. Like so. And the width again of each of these is 1. If I find the height is 1 there, 2 there, 1, 2, 3, 4, 5 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. So over here, when I'm estimating that same integral, I'm again finding the area of each rectangle, but this time it's 1 times 1 plus 2 times 1 plus 5 times 1 plus 10 times 1. So 1 plus 2 is 3 plus 5 is 8, 18. That's the main idea of this. There are just a couple of tweaks on how we figure out exactly how to do it. And the first question we have is, how do we choose how wide to make the rectangles? There are two ways that this can be presented. One is that we can be told an interval. The other is that we can be told a number of subintervals. This is what the two different questions look like. So if we're told an interval, it means we're going to estimate the integral from 2 to 6 of f of x dx using, and we have to be told which of these ones up here we're doing, using a left Riemann sum with intervals of, actually let's make this from 2 to 8, intervals of width 3. Whereas over here we're going to be told estimate same interval using a left Riemann sum still, and 3 sub-intervals. So here are little graphs. They're exactly the same for each. But what's going to be different is that right here we're going from 2 to 8. Over here we're going from 2 to 8. But here it says break it up into intervals of width 3. So I count over 1, 2, 3, 1, 2, 3. It should break evenly into widths of 3. And I'm using a left Riemann sum, so I'm going to draw up to the left corner is touching. Here I'm going to go up to the left corner is touching. And here it says use 3 subintervals. So however wide this is, 1, 2, 3, 4, 5, 6, I'm going to divide that by 3, which gives me 2, so that when I break this up, I get 1, 2, 3 intervals of the same width. Again, left Riemann sum, so I'm going to go up to the line on the left side, and there I've broken that down. Now, when we figure out these areas, it's exactly what we were doing before. We're going to do the area of the first one, so this is 1, 2, 3 wide by 1, 2, 3, 4, 5, 6 high. This was also 3 wide by 3 high. So the area of this first one is 6 times 3. The area of the second one, 3 times 3. Or 27. Here we've got a width of 2, a height of 6, a width of 2, a height of 4, a width of 2, a height of 2. So on this side, the estimate is going to be 6 times 2, the area of this, plus 4 times 2, the area of that, plus 2 times 2, the area of that, or approximately 24. There are a couple more tweaks we can see. One is, what if we have an equation instead of a graph? Basically, all that we have to do is turn this into a graph. So here's our problem. We want to approximate the integral from -6 to 0 of x squared dx using right Riemann sums and 3 subintervals. So the first thing that we want to do, I'm just going to write the steps over here. We want to roughly sketch it. It is important to know your parent functions, so if you have an x squared, you should be drawing a parabola. I should be able to mark the subintervals and draw the rectangles. And then you're going to find the height of f of x from the equation. So for example, with this x squared, we know that it's sort of U-shaped, something like that. That should be a little more curved. And we want to go from -6 to 0. So here's 0, -1, -2, -3, -4, -5, -6. We want 3 subintervals, so this is 1, 2, 3, 4, 5, 6. It's 6 wide. 6 divided by 3 is 2. So our subintervals are going to be 2 wide. And it said to do right hand sum, so the right side should touch. And it touches the curve. Here it looks like, and it should look like, that the curve goes through the point 0, 0 right here. So this is just kind of a flat line. That's okay. So what we need to do now is we're just going to find the height of each of these. So this is at -2, this is at -4, using this equation. So this height right here is whatever x is, so -4 squared, which is 16. This height right here is -2 squared, which is 4. This height right here, this x is 0, so it's 0 squared, which is 0. So then when we go to approximate our answer, antiderivative from 0 to -6 to 0 of x squared dx approximately equals, this width is 2, 2 times 16. This width is also 2, 2 times 4. And this width is 2 multiplied by 0. So it approximately equals, if we add all these up, 40. We've been calculating Riemann sums with rectangles, so our sums are generally either greater than or less than the actual area under the curve. In fact, there's a very specific pattern that we observe for when they overestimate versus when they underestimate. For overestimating versus underestimating. There are basically four situations, and they're different for whether we have a left sum or a right sum. So the first situation is we can have a decreasing function, or we could have an increasing function. We could also have either a left sum or a right sum. So a decreasing function looks like this, an increasing function looks like this, And so you notice if we do a left sum, so we're coming up here and the left side is touching, then the area inside the purple rectangles is greater than the actual area under the curve. So in this case, a left sum with a decreasing function overestimates. A right sum does the opposite. The right side is touching, and we can see that it underestimates. Here, it's reversed. A left sum, the left side is touching, that's an underestimate. Here, the right side is touching. It overestimates. And one of the useful things about these properties is that you'll notice that whatever we have, one of them overestimates and one of them underestimates. It's just reverses for increasing and decreasing. So that means that if you take both sums one will always overestimate, and the other will always underestimate. This allows you to do what's called bound the area. Or in other words, find the range that the actual value must be between. So this is really nice because even if we only are able to approximate the value, we can at least say that it's got to be between this value and this other value, which is very useful. Eventually, mathematicians would want to get much more precise than that. And so they developed a couple other techniques, one of which we're going to go over in the next lecture, and then we're going to go over the techniques for doing it very exactly in a much quicker and easier way in the following lessons. So we're almost done. I just want to put out a final check for understanding problem, and then that'll be it for these notes. So for your check for understanding problem, try this one on your own. Estimate the integral from -1 to 3 of x minus 1 with respect to x. I want you to use, using a right Riemann sum with subintervals of width 1. And then I also want you to answer, is this an overestimate or an underestimate? Try this on your own and restart the video when you're ready. Pause the video now. Okay, so here's what I did. I sketched it. Y-intercept is -1, the slope is 1. And then I sketched in my little rectangles. I'm making sure I'm using a right Riemann sum, so the right side of each rectangle is touching. And that means that in order to figure out the height for this rectangle, I had to use 0. 0 minus 1 is -1. Here 1 minus 0, or 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. Each of these had a width of 1, it said right there. So I just did height times width, height times width, height times width, height times width, got all these and added them up to be 2. Now our question is whether this is an overestimate or an underestimate. It's a little hard to tell with these negatives, but do remember from here a right sum and an increasing function is an overestimate. Also, we can kind of see that. We can definitely see the overestimate that's happening here. Here, less negative is being taken away than should because there are these little gaps here. So that means that this part is also giving us an overestimate. So it is an overestimate. If we wanted to, we could actually see what the exact area is because we know how to find this. This is 2 by 2. So 2 times 2 divided by 2 is an area of 2. And then we ought to be taking away this little piece here, which is also a triangle with a width of 2 and height of -2. So these two areas are actually equal, but one's positive and one's negative. So our actual answer ought to be 0. We can see this is definitely an overestimate. This concludes Integrals 1 notes.